So we'll move on to our next speaker. I'm very pleased to introduce you to Bernd Ensing. He's the director of the AI4Science Lab, and AI4Science is one of the inspirations, I think, behind some of the concepts and programs that we were doing in the Data Science Center, and really a leader in this area. So we're very excited to have you.
Thank you very much, Paul. So I guess I still need to use also my lecture voice, right? Yes, this is just for the online thing. Okay, understood. So yeah, let me start by congratulating Paul and Boy and Max and all members of the Data Science Center, and in fact maybe all scientists at the University of Amsterdam, because aren't we all, in the broadest definition, collectors of data and processors and of data, bits of data and information. And I think it's a great day for this kickoff. Could not have been more timely, I think. It's a super exciting time for this. And I'm super happy with this initiative. And why am I standing here? Because, well, as Paul was saying, yeah, the AI4Science Laboratory is somewhat related. It kicked off exactly 1 year ago. Well, the idea started more than 1 year ago, obviously, and I've been directing it since. And I will tell you a little bit about it, and hopefully also show a little bit of what we've learned in 1 year, let's say. You know, 5 years or so, if I would ask people around me, what do you think of artificial intelligence? What do you think of? People would think of this sort of things, and things have changed very rapidly. And now most people, at least, you know, my colleagues in the chemistry department and well, the Faculty of Science, actually can think of many ways of many things around them for, you know, applications of artificial intelligence in their daily life. So fortunately, we are in University of Amsterdam, super lucky, I think, with being at the forefront of developments in AI4Science, especially, of course, in the Informatics Center Institute, but also, yeah, all sorts of spin-off that you know about, you know, like this new building that is being put out of the ground. We're part of the European Laboratory for Learning and Intelligent Systems. Microsoft Research is setting up a laboratory here. And so there's many things happening. One I want to mention especially, that is this Innovation Center for Artificial Intelligence, the EKI Labs. It's not just in Amsterdam. It's now in many places, actually, in the Netherlands. And there's, I think, almost 30 of these laboratories that typically have 5 PhD students doing interesting research where they connect experts on artificial intelligence, machine learning, data science with problems that in all sorts of, you know, industries and also non-profit organizations, such as the police force in Amsterdam, for example, but also ING and BASF have these type of labs. So typically 5 PhD students doing interesting science. There's a lab manager and typically 2 directors, one an expert in data science at the Informatics Institute, and one with, you know, the domain knowledge of the company. Why am I telling you this? Because the AI4Science Center was actually initiated with that idea. So if we are so great with connecting with the outside world, we have lots of data within the University of Amsterdam, especially in the Faculty of Science. There's all, you know, labs creating daily huge amounts of science, and already in many domains, scientists are actually using machine learning and artificial intelligence tools. Why don't we connect these things? And so that was the start of the AI4Science Laboratory. I started this again with another director, so there were 2 directors, Joris Moy, who moved on, and we're actually looking now for another director. And Paul Foray is then the laboratory manager, let's say daily supervisor of PhD students, etc. So we are connected with all the institutes and, of course, informatics, together with, well, ecology, biology, mathematics, chemistry, physics, and astronomy experts. They gave us interesting projects that we made a selection out of. There was, so in initial phase, money for 5 PhD students. And these are all, you know, brilliant guys that do super interesting projects. So these are the projects that we started with in radio astronomy, looking at real-time data from radio signals from space, looking at gene regulation networks and causal relations in that. I will talk a little bit about this one. This is the chemistry project on spectroscopy, or well, I should say chromatography. And ecology, looking at bird migration in Europe. Can we predict how, when birds migrate? And this might be interesting because if we are able to do a good job, we can stop, for example, windmills in the sea that now kill lots of birds and things like that. And this project on gravitational waves, where we analyze data from the LIGO experiment. So apart from doing super interesting science, we also find it our mission to support initiatives within University of Amsterdam and outside, where we connect machine learning with scientific research. And so we set up a consortium. We're doing all sorts of things within this consortium. We're doing workshops. We have bi-weekly work discussions, and anyone interested can join in principle. We have now several associate members as well. We have a bi-weekly AI4Science colloquium series, which is until now still online. And actually, we like it so much online. It has so many advantages because we can get great speakers from all over the world. Sometimes we have to move the time a little bit. It's every second Tuesday at 2 o'clock because of, well, time zone problems. But this is a really super nice because open, and we get exchange of great ideas. So I will just talk about one scientific project that is just to give you a concrete example of something that we can do. And this is one that is really multidisciplinary. So Jim Mulrijk is a PhD student doing most of the work. Then Bob Pirog is an analytical chemist. He knows everything about the sort of experiments done by chromatography, using chromatography. Patrick Foray, the lab manager of AI4Science, has a very strong background in mathematics and machine learning. I myself, my background is in multiscale modeling and computer theoretical chemistry, let's say. And then what is also very interesting for this project is that we have a very strong connection with this company, Agilent. It's a Dutch company that actually makes these machines, these chromatography machine. I will show you one in a second. And they are really interested in this because chromatography is a very powerful analytical chemistry tool to analyze samples and separate chemical samples. For example, urine, blood, all sorts of things with thousands of components, and you're looking for what's inside. And this is a great technique, but it takes months of tuning the machine to get optimal resolution. And so that's a problem, and their machine learning could really help. And so they are so interested in it because they make these machines, and if they could connect it to software that does this optimization for them, then many companies would profit for them. And now they think, okay, that it's a great tool, but we don't have months to optimize it for our problems. So this is the sort of stuff that comes out of this machine, these 2D plots. Initially it looks like this, and then if you work on it, it starts to look better and better, and you see all these little peaks, and each peak is from a molecule. So if you're able to count the peaks, but even here they're all on top of each other. And I'll explain a little bit about this sort of data and what's the problem with it and what machine learning can do with that. So maybe you've done this sort of experiment actually in your chemistry class at high school, where you had to, with different colors of pens, make dots on a piece of paper, right? And then you had to put this paper in a little bit of liquid, and the liquid would suck up in the paper, and then it would make stains. And you would see that, yeah, each paint is actually composed of many components, and they would make these little dots, right? And you could separate them, and you'd say, oh, each dot is a chemical, right? So you always have this mobile phase, a liquid that goes up, and a stationary phase, which here is the paper, and that does the separation. So how many people of you feel that they are experienced with chromatography? Do you know about chromatography? I see a few hands. So not so many. I'm a little bit surprised because do you know what this is? It's liquid chromatography, right? So you make your drops in here, and then it will suck up in the paper, and there is a control chemical in there that should make a stripe at this distance. And if you're positive, then you get a second component there, right? So this is liquid chromatography. So yeah, the professional systems look a little bit different. They so here is one of these machines, right? So you see here the experimenter taking a syringe and injecting the sample in here, and it goes into this autosampler and then into a column, and then there's a detector, and it separates them in the column, and then one by one the components come out if you've tuned this well. So they're usually very small, these columns, and they have a high pressure to press this stuff through. And the way it works is this: so you have a solid phase, so like a tube, and there is some grains in there, and the molecules like to stick to these grains. And then you pump this liquid through, and some molecules like to actually dissolve in this liquid, and they come out first, right? So they will separate, and then there's a detector, and that gives you a little peak. So bleep, okay, there's molecules type first coming out, the first one coming out, and the ones that stick a bit more to the solid phase come out later. And so it depends very much on the interaction with the solid phase and the liquid phase, and it can select on, for example, molecule size. So maybe small molecules come out first, or bio-infinity, hydrophilicity, polarity, maybe charged species, etc. So there's many ways of things that you can separate on. And then there's lots of tricks. So this is very simplification, but one of the tricks that you can do is that you start with one liquid and then you slowly change it to another liquid. So you change the ratio during the experiment, etc. So there's lots of tricks, lots of dials to turn on. How am I doing with time? Should I speed up a little bit? Okay, excellent. Thanks. So now, so the thing is that, so even if you're able to separate on molecule size, for example, so suppose you are a doctor and you're looking for someone has cancer, and you inject blood sample, or maybe you're in a sports event and you're looking, did this guy take illegal drugs or whatever. Things may still come out on top of each other, right? So just selecting for one type of interaction is typically not enough, and so that's where the 2D comes in. Right, so we have here one, and then stuff comes out here, and then it goes into a second column, and then there's second separation on a different property, right? And so here's in more detail. Here you have the first one, and usually the first column is slow, right, on the order of minutes, let's say. The peaks come out, and then each peak here is collected, and then it goes into a second one, and then that peak is separated again, and then a little bit later, a new peak comes out, it's also separated again, and that then goes fast. So it goes quicker in the sort of fast one. The second dimension is usually fast. And then you get these two-dimensional plots that I showed you in the beginning, right? So now what Jim was doing together with Patrick is say, a great way to do this sort of optimization in high-dimensional space, where you have many dials to turn. Let's say you have, so here we started with 8 different parameters that we want to optimize, is using Bayesian optimization using Gaussian processes. And we select for, maximum orthogonality. So there should be the least coupling between the first and second dimension, and the highest resolution. So can we see as many peaks separated per time? And so I won't go into details, but so the machine learning methods that we use is Gaussian processes, which is doing a compromise, or finding the best balance between exploring different settings. So not doing like a steepest descent and getting stuck in a local minimum, but see where can we quickly go in parameter settings where we have a large uncertainty, versus exploitation, which is okay. Which where do we think is the optimal value? Let's go there quickly. So okay, this is for if you have questions about it. I will skip it for now. But one important thing is that to make this sort of methods, it was very nice that we had actually a simulator, because an experiment takes time. Moreover, these things are used all the time. these machines by the students of Bob Pirog, and so we actually had a simulator, so we could do thousands of experiments in a very short time. So that was very nice. And lo and behold, this method that Jim developed works really great. So on samples of with 50 components, the Bayesian method always did much better than well, trying randomly, for example, or doing a grid search. And moreover, with only 100 experiments or so, he almost always found solutions that are better than grid search. And imagine this is in 8 dimensions, right? So even if you take only, let's say, 5 steps on a grid in 8 dimensions, you have like 1 million or so experiments to do, right? So you can imagine the speed up. So that paper is now under revision, and especially the company is super happy about it, and of course we are as well. So conclusions are that this works great. The machine, the algorithm is now coupled directly to the machine, thanks to the company who says, oh, that's great, let's connect the robot to it, and then the computer can talk directly to the machine and do many experiments automatically using this Bayesian optimization. So that's thanks to this company, so that's really great. And of course, we have lots of new ideas because from both sides, both from the the machine learning experts and also from the analytical chemistry, we see opportunities of well, can we also detect how peaks move if you turn the dials? Can we already predict where a peak will go? Can we detect artifacts in the spectra? And a holy grail would be, can we actually learn structure property relationships? So can we actually learn something about what are the properties of these molecules that are inside, based on what we know of the sort of interactions that they have with the machine, with the stationary and the liquid phase. Okay, I should round up. So after 1 year, I want to say a few things about what we've learned so far from this sort of multidisciplinary collaborations. So first of all, some challenges. First off, I would say data science, or artificial intelligence as well, is super broad. And so it's not so easy to find overlap and coherence in the lab. So we already, when we selected these 5 projects to start off with, we tried to find coherence and overlap between the projects. I think we did a reasonable job, but then still it's not so easy. And so it could be that the critical nucleus, to have a good collaboration in the lab is big. So in the end, you will actually have subgroups of people that can work together because they do very different science, but maybe in the methods there are overlaps or vice versa. And that also counts for example, other things that we do, like our bi-weekly colloquium series. Sometimes we have lots of people coming online, but sometimes we have a great speaker, but he's working in a niche, and then the audience is very small. And so we find it still hard to predict, simply because, well, it's such a broad field, I would say. Another thing is, I think it will be challenging also in the future to stay inclusive and multidisciplinary. I mean, that's of course the aim. I mean, that's how we start off. But you feel sometimes the forces pulling a little bit on the lab, and it would be really a pity if, for example, it will go more in one direction than in the other direction. Also, because very much is what we do is driven by funding, simply because it's such a competitive field, which means that the scientists that want to collaborate with us, so everyone wants to collaborate with us. And we also see that, we heard that in Paul's talk, if you see 70 applications or more for this 7 PhD student positions. But that is also because it is so competitive, right? And that means that if the funding at some point would stop, and we have funding for 5 years, and of course the idea is that after that, people are aware of how successful this is and will do their best to acquire their own funding, etc. And that's of course what we do. But since it's so competitive, that may not happen. That may turn out to be difficult. And then if scientists, they may, they try everywhere to find funding. And then if they get funding somewhere else for another project, they will do that, simply because in such a competitive world, that's unfortunately how it works with current funding schemes. So I think it will be important, to be careful not to dry up the funding too quickly and make these sort of labs stand on their own feet. Now, there are also lots of opportunities. So first of all, the science that comes out of this is great. So it's super nice to have multidisciplinary groups, collaborations, because the ideas that come out are really brilliant. I don't think I have to convince you of that. And so it's very nice how it connects different fields and disciplines. I also see a sunny future for data science and AI4Science together. There's lots of overlap. I think they're very complementary, and so I'm really looking forward to collaborating. And also we have great opportunity to attract great people. So great scientists, obviously, but also great scientists. They may come to Amsterdam because they see that the developments on data science and machine learning are great, and many people would love to work on machine learning development, but I think there's many people that would like to work on physics or chemistry with machine learning, and not really machine learning developments per se, for example, or data science developments per se. And so I think we can take a big role in that, but also for industry, non-profit, other stakeholders, and policymakers as well, I would say. We do our best to support attracting funding. So even if people don't want to collaborate with us, with AI4Science per se, but they say, I have this great idea. I know it will be difficult to get funding from NWO because we're just starting. We're not experts yet with machine learning. Can we use your name and say that we're collaborating with you? I'm super easy with that. I always say yes. Maybe we'll start a collaboration, maybe not. But I know by myself, from my own experience, how difficult it is as a chemist to get money to do machine learning, because, well, you're a chemist, you're not a machine learning expert, right? But if you are collaborating with AI4Science lab, that looks really good. So we're always trying to help there, and also helping with writing the proposal, etc. I think we should really take a big role in student education. I'm now making a master course in chemistry, actually, on machine learning in chemistry, and next year there will be a bachelor course as well. And it's great to work with informatics people that are teaching this stuff already for many years, and exchange and learn. And finally, I really think that we have an instrumental role, data scientists, artificial intelligence, machine learning experts, in solving key problems that are super important for society today, related to energy, sustainability, the plastic problem, you name it. And so I think there's great opportunities to do great work there. So thank you very much, and that's what I want to tell you.